Hello. Today I want to talk about a special kind of relation called an equivalence relation.
Not until you run Windows Update. You haven't run Windows Update in 9 months.
I know, Roz. Can I get back? I'm filming a lecture.
Don't let it happen again.
She gives me the quakes. Equivalence relations are a special relation. Right? Relation on A, R on A is said to be an equivalence relation if and only if what? Well, if the relation is reflexive, symmetric, and transitive. So here I just copy and pasted these three definitions from the previous video where we defined these ideas, reflexive, symmetric, and transitive. So that's all equivalence relation means. It just means that R is all three of those: reflexive, symmetric, and transitive. That makes R an equivalence relation. So why is it called an equivalence relation? Well, because the most famous example of an equivalence relation is equals. So, right, so if you take, let R be the relation equality, right, on basically any set you want. Let's say, how about the natural numbers, right? Just for sake of picking one. So what can you say about this? Well, why is it reflexive? Well, every natural number is equal to itself, right? So it's reflexive. If one number equals another, then automatically the other equals the first, right? And if one number equals another, and then that number equals yet another, then you know that the first is equal to the third by substitution, right? So this is reflexive, symmetric, and transitive. That's why they call it an equivalence relation, because it behaves like equals, right? So thus, you could say that equals is an equivalence relation, right? If it weren't, we would have picked a bad name for this concept, right? So this is our kind of canonical example of an equivalence relation. To give an example of something that is not an equivalence relation, in the previous video also I talked about divisibility, right? Divisibility is not an equivalence relation, right? Because it's not symmetric, which is something we talked about in the last video. Right? Even though it does happen to be reflexive and transitive, it's not symmetric, so it's not an equivalence relation. So there's an example of a relation that is an equivalence relation, and an example of a relation that is not an equivalence relation. Why do we care so much about equivalence relations? Well, it turns out they have a really important connection to the idea of partitions. So that's what I want to define. So a partition of a set A is a collection of subsets of A, which that collection, we'll call that A1, A2, up to AN, right? And in truth, this is actually a set in and of itself, right? It's a set of subsets. So the collection of subsets of A such that the following hold. We need the union of all of those sets to equal A. So it's to cover all of A. And they are disjoint. Right, so if you pick two distinct indices from 1 to n, call those I and j, right? If I pick two different of those sets, a sub I and a sub j. You don't just pick a sub I and then the same a sub I, right? The actual distinct ones. That is going to give you a disjoint intersection, right? Disjoint sets, right? An empty intersection, which means just the empty set for intersection, meaning there's no overlap, right? And in this case, just a little bit of language. In this case, the sets A1, A2 up to AN, those are called the parts in the partition. Right? So this is the definition that we have here, right? So we define the term partition and parts of the partition, right? And no, why is this called a partition? Well, a good perspective on this is actually to think of that Venn diagram kind of perspective. What does it mean to have a partition? Well, here's, say, some set A, right? This is a set A. And now I want to see visually what does a partition look like in a Venn diagram. So it's a collection of subsets that together comprise all of A, but pairwise do not intersect, right? That they're all disjoint from each other. So what you could imagine here is that a partition is a way of cutting A. So this is our set A. We cut it, however you might cut it. Maybe this is say this is this whole thing, right, is the set A, right? But then I cut it up now into all these subsets, A1, A2, A3, A4, A5, right? I chopped it up. And so A collectively is the union, at least how I have it drawn here. See, big A would be the union of all of these 5 sets, right? But also the way I drew it here, there's no opportunity for these sets to intersect each other, right? I didn't draw, A1 and A2 like I usually would draw 2 sets where there's some region where they might overlap, right? I purposely drew A1 and A2 as not sharing any region, right? So they're non-intersecting just by how I have, you see that they're not intersecting by how I have them drawn in the Venn diagram. So this would be a one visual representation of what a partition might look like. This kind of shows why you might call it a partition. Talk about maybe in a room when you say, "Oh, I'm gonna." If you're in, say, one of those large classrooms that's like a double classroom, but there's a partition in the middle that can turn it into 2 small classrooms, right? You sort of just pull that wall across the classroom, and now it's been partitioned into 2 parts, 2 smaller classrooms, right? And that's kind of what happened here in our Venn diagram. We just sort of ran some walls across, right? We built some partitions, and that gave us a partition of our set, right? So that it's partitioned in that same sense. Now, let's look at a little example of this. So for example, let's think about an equivalence relation. And I want this relation to be where 2 integers, we relate integers, and I'm going to say that 2 integers are related if and only if they have the same absolute value. That's going to be my relation. And notice here I've flipped back to talking about relations. Why? Well, because I'm trying to connect equivalence relations to partitions. And I think a small example like this is maybe the easiest way to see this connection. So what do we have here? Well, if you think about the integers, right, the set of integers and this relation, right, what kind of integers are related by this relation? Well, I would have, for example, 2 is related to 2. Well, because absolute value of 2 equals 2, right? Also, 2 is related to minus 2, right? Also, minus 2 is related to 2. Also, minus 2 is related to itself, right? These are all true. These are all true claims, right? So if you want, you could imagine drawing this. I was not expecting that. You can imagine drawing this, there we go, where we have this set Z, right? And you can imagine drawing this where you say, okay, 2 is related to itself, right? Minus 2 is related to itself. 2 is related to minus 2, and minus 2 is related to 2. You can imagine drawing it like that, right? That's, those are some relations that are, some pairs of elements that are related under this relation, absolute value of x equals absolute value of y. I can also do it with 3, right? 3 is related to 3. What else would 3 be related to? 3 would be related to minus 3. 3 minus 3 would be related to 3. Minus 3 would be related to itself, right? So I get a very similar looking picture here. Okay, 3 was related to itself, minus 3 was related to itself, 3 was related to minus 3, and minus 3 was related to 3. There we go. Okay, this is pretty clear how this is going to go. So I'm drawing all of the relations here, right? And 1 has another similar looking picture, right? And 0 actually lives by itself here, right? 0 is only related to itself. So now if you look at this, man, you can say, well, and one thing we should note is this relation is an equivalence relation, right? Every number has its own absolute value, so it's reflexive. If absolute value of x equals absolute value of y, then the absolute value of y equals the absolute value of x. It's symmetric. And also if absolute x equals absolute y, and if absolute y equals absolute z, then absolute x equals absolute z. So it's transitive, right? So this is an equivalence relation. Now look at this blob diagram that we drew, showing all the arrows to show all these relations. Well, man, no one, it got tedious of drawing all these arrows each time, right? An easier way to represent this would be to just do this, to just partition the set into subsets where each subset shows all the elements are related that are related to each other, right? So 0 is only related to itself. 1 and minus 1 are related to themselves and also to each other, but to nothing else. 2 and minus 2 are related to themselves and to each other, but nothing else, right? So you're imagining just sort of putting up those partitions between these clusters of elements that are all related to each other. And because it's an equivalence relation, you know you're never going to have, say, something like this, like one arrow that kind of just jumps out from one part into another part. It's never going to happen. Because if minus 2 were related to minus 4, it would then automatically also be related to 4 by transitivity, because A relates to B and B relates to C, implies that A relates to C, right? So this will never happen. The two parts will always either be, you'll never have just sort of one lone arrow that goes rogue and leaves its partition, right? Because we're dealing with an equivalence relation. So this is a really nice correlation, right? I have this relation, this equivalence relation. Well, I could encode that equivalence relation by this partition, right? And so that's what we're seeing here is there's a correspondence between an equivalence relation and a partition, right? If you handed me that partition below, I could build the equivalence relation by relating all the elements that live in the same part together, right? If you handed me that equivalence relation, I could build the partition by just putting walls between the clumps of elements that are all related to each other, like I did in this diagram, right? So this is super cool correspondence, very, very useful in mathematics. This comes up all the time in like basically every branch of mathematics. I can't think of any part of mathematics that doesn't somewhere use equivalence relations and use this idea of the correspondence to partitions. So let's now say this a little more formally, right? What are the what exactly are the parts of this partition? So this relation that we've been talking about, absolute value x equals absolute value y, this relation R induces the partition Z equals, I'm going to call them these sets A0, A1, A2, A3, A4, and so on. So Z here would equal A0 union A1 union A2 union A3 union, and so on, where A0 is the set just containing 0, and then AN equals the set containing just n and minus n for all natural numbers n, right? That's our partition, is that collection of subsets, right? So we have one with just the single element 0, and then all the other subsets have two elements, right? A natural number, positive natural number, and it's negative. So there we go. There's a partition. The parts of the partition are called the equivalence classes of the relation that they came from. Right, so this is a term that you'll hear a lot, equivalence classes. But the equivalence classes are the parts of the partition that came about as a result of the equivalence relation. Right? So this is a theorem, a super useful theorem in mathematics, right? Is that every equivalence relation induces a partition. How? Well, by just dropping walls between the clusters of interrelated elements, just like we did. Right. And vice versa, every partition induces an equivalence relation. How does it go the other way? Well, you just define your relation to be that x relates to y if and only if x and y live in the same part of the partition. So I want to show an example of going the other way, right? The first example that I gave here was an example where we started with a relation, with an equivalence relation, and then we found the partition by putting up those walls. Let's go the other way. Let's go the other way. So let's do another example, very simple example, where I'm going to give partition. And let's find the equivalence relation induced by the following partition. And here I'm going to do a finite set. So my set A is just going to be the letters A through E, right? That's my set A. And the partition is going to have just two parts. One is going to be AB. One part is going to be C, D, E. Those are going to be the two parts of my partition. Notice it's a valid partition because A1 union A2 equals A, and A1 intersect A2 is empty. Okay, so let's now look at what equivalence relation this would induce. Well, I think this is where it's often convenient to, again, draw this blob diagram. So what do I have? I have on this set A, I have little a and little b living over here in A1, and then I have C, D, and E living over here in this set A2. So A has to relate to itself, B has to relate to itself, A has to relate to B, and B has to relate to A. C has to relate to itself, D has to relate to itself, E has to relate to itself, D has to relate to both E and C, E has to relate to both C and D, and C has to relate to both E and D. There we go. And there are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 arrows in this relation. Did I count wrong? I think I counted wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, I didn't count wrong. Oh, right, because it's 4 plus 9. Yeah, it's 2 squared plus 3 squared. Right. So yeah, that's right. So there are 13 relations here. There are 13 connections between elements, right? If you wanted to write out the relation longhand in sort of as a subset of A cross A, you could, right? We've 13 elements started out. So it's a little tedious, but just to really show what that relation is, I think it's worth it. So AA, AB, BA, BB, right? C, C, CD, CE, D, C, D, 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 E, E, C, E, D, and E. And this should be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There we go. The 13 ordered pairs in this relation, right? So it's a finite set, finite. There are only finitely many possible ordered pairs, right? There were only 25 possible ordered pairs from the set A with 5 elements, right? And 13 of them happen to be in this relation that's induced by this equivalence relation. All right, great. So that's the big important theorem, right? Which you will see a lot in mathematics, right? Every equivalence relation on a set corresponds to a partition. Every partition gives you an equivalence relation, right? The parts of the partition are called the equivalence classes, right? So like here, you would say that R, this relation R, has equivalence classes consisting of the subsets A1 and A2, right? Just the sets we were given from the get-go, right? So it's just the sets of elements that are all related to each other. That's what the equivalence classes are. So there we go. R has two equivalence classes, A, B, and C, D, E. Great. Thank you so much. See you next time.